So first of all, I thank the organizers for the invitation, and also everyone from Newton Institute for the excellent time I have here. So 2 weeks ago I was talking about accelerated schemes, but in that case the schemes were in the spatial variable for stochastic partial differential equations. It was shown that Richardson idea of accelerating numerical schemes by playing with the parameter can be used, can be applied to stochastic partial differential equations. Today I would like to continue that, but now with respect to the time variable. And in fact mostly that will be, the idea will be applied to random partial differential equations. You will see the difference. Well, the talk is based on joint result with Nick Krylov. So this is the plan. So first an introduction that where using Wong-Zakai type results, stochastic partial differential equations are approximated by random partial differential equations. Then a class of time discretization schemes are formulated in form of differential equations where the driving process is a periodic process, and that is what I call equations with periodic controls. And finally we will show how these types of numerical schemes can be accelerated by using Richardson idea. So what we consider, what we are interested in is strong approximation of linear stochastic partial differential equations of the type which is written down, like the Zakai equation for nonlinear filtering, where W is a multidimensional Wiener process, L is a partial differential operator. In most of applications it is second order, but it can be higher order as well. But as in the Zakai equation, it is a second order elliptic operator, and Mi are first order operators, and the Cauchy problem, so initial value problem, is considered. Now in practice, in place of the Wiener process, we usually have some approximation of it. For example, when that is the observation process, then due to the measurements, instead of the ideal observation process, we have some approximation of it. So imagine now that instead of W we have Wn, which is a process of finite variation. Then some well-known results on Wong-Zakai approximations are as follows: that if Un is the solution of the equation where the W is replaced by Wn, and the equation is written in the so-called robust form, so that means or the original equation is written in the robust form, and then the W is replaced by Wn, then we have such a problem where the L tilde operator is decompensated with the 1/2 mi, which is the summation with respect to the repeated indices I, and F tilde is also compensated. Then it is known that if the Wn converges to W uniformly in the time on a bounded interval 0 capital T, and Sn, which is defined here, so the area process corresponding to the coordinates of Wn converges to the area process corresponding to W uniformly in T, and if the first variation of this Bn process, which here there is a mistake that there must be here an n, so this is just an integral with respect to a process of bounded variation, so here there must be an n. Then, under these conditions, the above conditions, we have that if those conditions are satisfied in probability, then we have the convergence also in probability in appropriate norms. For example, in Sobolev norms, uniformly in T, provided that the coefficients and the data, the initial data and the free data are sufficiently regular and the stochastic parabolicity condition holds. Moreover, if one has rate of convergence estimates for the convergence of Wn to W, Sn to S, and concerning the boundedness of Bn can be weakened. So suppose that almost surely the convergence is ortho n to the minus kappa for some positive kappa, and similarly for the convergence of the area processes, and if the first variation of Bn is small ortho ln or ln n, almost surely, then one gets that under these rate of convergence conditions, one gets essentially the same rate of convergence for the solutions, or rate of convergence of the approximations un to the solution. Here this norm is provided the coefficients and the data are sufficiently regular and the stochastic parabolicity hold. So this norm here depends on the regularity of the data and the smoothness of the coefficients. So the results are in Sobolev norms, also using the method of characteristics. Results have been proved by Gislav and Franco Flandoli when the approximation is the polygonal approximation for the W with the Wn. Well, so having in mind these approximations, one can approach to approximating stochastic partial differential equations in two steps. First, using a Von-Sakai approximation, the type which are formulated here, and that there is already an error, but then further on we have a kind of random PDEs, because now the driving process which replaces the W is a process of bounded variation. So for each omega we try to solve this equation and apply numerical methods to this. So in my talk I will give some results about the numerical methods in time, how to accelerate what is the rate of convergence and how can one get better rate of convergence when approximating this equation. So the first, I am going back. Moreover, here assume that the driving process is absolutely continuous with respect to the Lebesgue measure on the time interval, and then for each trajectory of the driving process, in fact, we have to solve this kind of deterministic when for fixed omega PDE by a numerical method. Right, so I would like to show how to describe a class of of numerical methods in the time discretization by a class of equations. So to have a general framework, let us consider this equation here with initial condition in a sequence of separable Banach spaces where these V naught VL for some L greater than or equal to 0 are Banach spaces such that Vi is continuously embedded into Vi minus 1. So the situation is the following. So we have VL minus 1, V1, V naught, and we consider this abstract equation dut equals LUT plus F dt with initial condition. And this is the equation or problem, we refer to it as EQ later. We assume that L is a linear operator such that it is a bounded linear operator mapping from from each of these spaces. So when I is running through from 0 to, in fact, here L minus 1, if one writes it down, and F, the free data and the initial condition are elements from the smallest space VL. Then an obvious definition, a V1 valued weakly continuous function is called a solution if the equation is satisfied in the integral form where it is understood in Bochner's sense. Now some examples. The favorite example here is when L is a second order partial differential operator, which is parabolic partial differential operator. So Aij is a non-negative definite matrix. K is a fixed constant. The coefficients are differentiable up to order nu. K is a fixed constant, and the initial and the free data are in the Sobolev spaces W mu P. Here P is a fixed number greater than 1, nu is an integer greater than or equal to 2, and under these conditions one knows that there exists a unique weakly continuous W nu P valued solution of the equation EQ. And if we set Vi to be W mu 2I, P is missing, then we could cast this example into the abstract equation. The next example is a parabolic system of PDEs. This example is very similar. The difference is now that the unknown function is a vector valued function, so a function with values in R, Q, and the operator L is just is of the same form as before, but now A sub I and A are matrices, so they applied to the, so I means derivations with respect to the i's coordinate, and alpha beta means that those are applied to u beta and then we get the u alpha coordinate in the system. Similarly with A, and aij for fixed I and j is just a scalar, so we multiply the unknown vector when we take the second derivatives, each of the coordinates, by this scalar. Take p equals 2 and use the following parabolicity condition here. So there exists a constant k such that this inequality is satisfied for all lambda and x and alpha beta, where the a bar is the difference between, so the symmetrized matrix in alpha beta for each I. One can see that if this assumption is satisfied, if the matrix aij is uniformly non-degenerate. In this case, the system is a uniformly parabolic system. And if here the bar is missing, so here the bar, so if this equals 0, then obviously it is satisfied. So in this case, that means that the matrix if this is 0, so that means if we have degeneracy and AI is symmetric, so there is no mistake here. If AI is symmetric, that means that the left-hand side equals 0, then obviously the condition is satisfied. In this case, it is called a first-order symmetric hyperbolic system. So one can show that there exists a unique vector value with coordinates in the Sobolev space, weakly continued solution. And again, if we use if we set Vj as given here for fixed non-negative integer mu, such that this is satisfied, then we cast this system into the abstract equation. Right, so these are just examples for the simple abstract equation. And now let us see the approximation schemes for this equation. So in order to define the approximation schemes, so the approximation schemes is based on approximation of the driving process T. So in order to define what kind of approximation there we consider, where we take some right continuous functions with finite variation on each interval HR for some r running through running through from through the integers 1 to m. Assume that it starts from 0, and assume that the differences, so the differences are the same with period 1, and that at 1 it is 1, just to fix the value at 1. And for each tau, this is the approximation parameter, we define a transformation of this, a scaling of this HR or these HR functions, and the notation is ART for that. So that is a kind of approximation. So HRT is an approximation for T for each R. Another object in this approximation is a linear, or more precisely, not one but many. So here there there must be an R as well. So linear operators, bounded linear operators on the space V1, they are bounded operators for each I on the space Vi as well. And and this Vi, boldface Vi, is the space of Vi valued weakly right continuous functions having left limits. And now the approximation for that equation is defined as dWt equals Lr theta Rw plus Fr dRt, and W0 is the initial condition. So this is the approximation where we assume that L is the sum of M operators, linear operators, and F plus F is the sum of elements F1, Fm from VL. And this system, so this is once again EQ, and this is denoted by N. So this is our numerical scheme for the approximation of EQ. So these LR are linear operators, bounded linear operators. And in each space, so mapping from Vi plus 1 into Vi for each I. And let us see what kind of approximations we can capture by this scheme. So let us use the notation T tau for fixed tau for the grid, uniform grid in the time and then we can see that, for example, the finite differences in time can be cast into this scheme. Indeed, if we take m equals 1 and then just one operator and the h1, let me write down, and the hr is the driving function which is of finite variation and shift invariant. So more precisely, you remember that it has this property, and then just to recall the notation, the ART is tau times HR T over tau. And so we take H1, which is the integer part of T, and the theta 1 is the identity. Then it is easy to see that the corresponding equation is the implicit Euler scheme. If the operator still assume that m equals 1, we have only one operator theta 1 here, and use this operator where phi t minus is the left limit and theta is a fixed real number. Then n is the theta method, and we know that at half, when theta equals half, that is the Crank-Nicolson method, and if theta equals 1, then we have the implicit Euler method. A more interesting example is the splitting up approximation. So that means we have several operators. So we split L into the sum of the L1, Lm as there, and also F1 plus Fm. And we solve the equation on the grid with step size tau such that we consider the splitting up equations. So dv equals Lr plus Fr dr with some initial condition phi. So for this is the solution is denoted of this equation is denoted by P R. Is that the R is? Yes, P R T phi. This is the solution. So we solve in order to get the approximation. Once we have it here at Ti, to get the approximation at Ti plus 1, we solve the equation with initial value W Ti, and we apply so the solution with this initial value of this problem is denoted by PR tau. So in this interval Ti from Ti to Ti plus 1, and we do this for for each r from 1 to m, one after the other. So once we got the value of the solution of the first equation at Ti plus 1, then we take that as an initial condition for the second equation. Again, we solve, and then again and again with all. So this is of course not r but t for all r from 1 to m. And finally, when we have run through all the equations, then we get the approximation at time Ti plus 1. So that can be written down like this, where I use the notation W instead of the, here I use the notation W. This corresponds to V Ti plus 1. Well, now how can we represent this? So instead of going back and forth in time, we rearrange this method in forward time by stretching out the time interval, and then synchronize the time such that the synchronization is done at the grid points only. So if we do this procedure, then we can describe the at the grid points the approximation by this equation. So the solution of this equation at the grid points equals the splitting up approximation at that grid point as it is defined there. So how to see this? Maybe just to take two equation. So m equals 2, and then rearranging in forward time is take this tau interval, that second tau interval, and the driving process. Consider this driving process, which can be described like this, that here it is it is the identity on the first interval, then 0. This is one driving process. Let us call this B1t, and then continue periodically. The second is here, 0, and then the identity, and then periodically with period 2 tau, and here also with period 2 tau. And then if we consider now the equation dv equals L1 v plus f1 db1t plus L2v plus f2 db2t, then by this equation we describe the splitting method in forward time, but then we stretched out the time, so we used twice as long in order to be able to rearrange in forward time. So we should rescale, and by rescaling, in fact, we can see, one can get this equation. Rescaling means that to get the synchronization with the time of the original equation which we approximate. So this rescaling is then gives us the equation which I have mentioned, so that type of equation. And so on. Generalization is of this method, or seemingly a generalization, is the fractional step, which is just a splitting up method, but in p cycles. So for a fixed p which is greater than or equal to m, we run through this p times such that we do not spend the whole, when we use the equations one after the other, we do not solve necessarily on the whole tau, but only a portion of it, and that portion is are these S1, SP portions. And of course, we need to have that for each equation, we spend the portion, the whole portion. This is the assumption here. Well, and then once we have one cycle, so this product, then that corresponds to how to solve from here to the next point. And if we would like to get the solution at a fixed t from the grid, then we should do this procedure t over tau times, so then this gives the approximation. One can describe this fractional step method by using, or we describe this by using these functions kappa r, which describe one after the other how many, the portion of time the R operator or R's equation is used on each cycle. It is called symmetric if it is of this kind, or abstractly if the time derivative is symmetric, so with respect to reversing the time on the interval 0p. And the well-known example is the strength product. You see the symmetry here. P1 is applied on half of the time and so on up to Pm, and then half of the time, but now in the opposite order. One knows that these kind of approximations have better property concerning the accuracy. One can again see, just like before, that these kind of approximations can be cast into the form written there. Right, one can also combine the various types of approximations, for example, the two before, so the fractional step methods and the finite differences, such that in each step, when we use the splitting up method, we use a theta method to solve numerically the splitting up equation. And again, it can be written into the form which we have there. Now, about the accelerated numerical schemes. As we discussed last time, Richardson idea is based on the possibility of expansion of the approximation with respect to the parameter in the approximation, so the step size in our case in tau. So our aim is to show that there exists under some conditions such an expansion, so an expansion in power series of tau, where V naught is the solution of the original equation to be approximated, V1 and so on, Vk are functions independent of the parameter tau, and the remainder is approximated on the grid by a power k plus 1 power of tau, where n is a constant, obviously independent of tau. To formulate the result, let us remember this notation. dw means the weakly continuous, so weakly Cadillac processes, weakly Cadillac functions of the time with values in a Banach space V, and the C is the continuous, and the W is again for the weakly continuous. And in time, it is equipped with the supremum norm. Now I formulate some assumptions. So the assumption 1, that the operators LR are bounded operators from Vj1 to Vj. Here k is a constant. The initial value that we have already seen must belong to VL. The free data must belong to VL, and also we have this, if we would like to understand the dependence on the constant of n in the estimate of the remainder, then we fix here also the same constant k. Second assumption is that there exists a solution of such equations. So we consider nearly the same equation. So with this equation, but for the free term, we take any g from that W1, which is the V1 valued Cadillac functions, weakly continuous Cadillac functions, and here the all possible driving processes which are in the scheme of approximations. So there exists a solution of this, and the solution is denoted by this script Rk, and it is assumed that these Rk operators, which are linear operators, are continuous, bounded operators these norms. Moreover, the uniqueness holds as well. Once we have u from W1 which satisfies this equation, then u must be of the form defined by this Rk. Finally, that for each tau, the problem here, the scheme must have a solution. Also, the original equation must have a solution, a unique solution, and moreover, we must have a non-explosion in tau assumption for the approximations written here. When I write this L, that means this is the norm in the space VL. And now the main theorem is that let k be an integer, non-negative integer, and assume that the previous assumptions 1 to 3 hold with some L which is large enough, so twice k plus 1. Then there exist functions from W0 independent of tau, and the remainder term is also from W0, such that for all tau the expansion holds on the grid. It's important to emphasize we have this kind of expansion only on the grid but not everywhere. This is an essential difference in the previous talk I had 2 weeks ago. Well, so where V naught solves the equation and the remainder term has the desired estimate with constant n independent of tau. So this is the main theorem. And then obviously, as we have seen, once we have an expansion, this is the idea of Richard von, then taking suitable constants and different parameters, here we divide by 2. This is a convenient way of choosing the different parameters. So here that means that this is the approximation corresponding to the parameter tau over 2 to the j. So this rho j are defined like here, where V is the Wanderman matrix, defined like here. So we can consider this kind of approximation, so a mixture, such that by this mixture, when we consider for each of them, we consider the expansion, we can see that rho j's are chosen such that in the expansion for this, the lower order terms disappear. So therefore, one gets that the mixture approximates with accuracy k plus of order k plus 1. Now it's also interesting to investigate the coefficients, or the functions v1, v2, and so on in the expansion. And we can see that in the example 5, this example is the fractional step method. In that example, if we consider that example and the corresponding functions kappa, which describe the method, then the v1 can be given by this integral multiplied by r dij. R is the operator which corresponds to the original solution with 0, the solution of the equation with 0 initial condition. So r vi j is the solution of this equation with 0 initial condition and free term given here. where Li, Lj are the operators in the scheme. And so one can see that this V1 vanishes if this integral equals 0. So that is important to have methods where many of the coefficients are vanishing, because then we need less term in the mixture to get the same accuracy. So obviously that condition is equivalent to, not so obviously, but one can see that it is equivalent to this condition, and this can be investigated, and in this way one can find several types of methods for which the first term, or let us call this the second, the first is V naught, the solution of the equation. So the second term vanishes. One can see that that always vanishes when we have a symmetric method, a symmetric product like the strength method. But one can also see that there are infinitely many non-symmetric products. So one can figure out here many examples such that this is satisfied and the method is non-symmetric. So Strang's method is, or Strang's product is, only one of the many possibilities. And finally, going back from the abstract scheme to the examples, one can see that the parabolic PDEs and the systems of parabolic PDEs, which we consider in the examples, can be, so for them we can get these results, because these assumptions 1 to 3 can be ensured by suitable regularity, so smoothness and boundedness conditions on the coefficients and initial conditions and free terms. I don't want to formulate the consequence, it takes too much time, and so the shortly, the consequence is that we can apply the abstract results to these examples, and in this way we can get accelerated convergence results for these schemes. And moreover, just a final remark, that having these results for parabolic PDEs, which can be degenerate. So in fact, we have first order PDEs in our examples. So having accelerated numerical schemes for them, we can get similar results for nonlinear ordinary differential equations by the method of characteristics, deterministic characteristics. And I think that my time is roughly over. So thank you very much for the attention. That's all.
Thank you very much. And time for questions and comments. I would like to start. Are your results applicable to SPDEs with boundary conditions?
Boundary conditions. This abstract scheme can be used. Though in the examples we haven't worked out examples, but this abstract scheme can be used to those cases as well. So with boundary conditions.
This to SPDEs. Because this is random.
Random PDEs, yes.
Do you have any hope to extend?
Yes, thank you, Arno. Yes, so there is an obstacle. So it depends what is given when we have the SPDE, how the noise is given. If we have the noise given only at the points of the grid, then we know by Clark result that in general we cannot have, when we have a uniform grid, let's say step size tau, then we cannot have convergence faster than square root of tau. That's a nice result, which is valid also here. So this result was proved by Clark, or given an example for SDEs. So, but of course that is used here. So that means, in general, if we have knowledge only at about the noise at the point of the grids, we cannot accelerate. That is one thing. But we can have other information. So we can have if we have the iterated integrals, stochastic integrals, of course, then one can have using the iterated integrals, one can accelerate, but I don't know whether practically is so good. And another possibility, if there are commutators vanishing, then one can also show that acceleration is possible, but again, maybe practically not so useful. So there is this general fact shown first by Clark, that in practical situations we cannot really, unless we had some special situation, we cannot really accelerate in time SPDs. This is why I started immediately with von Zakai's, that let us approximate the noise, as practically we always have only an approximation, and then the random PDE is already very good to do everything what we want.
I have a question to Istvan and for myself.
Okay, then you should answer it.
I don't know. So the idea is to first approximate SPDE, smoothing the Wiener process, and so that we will come to ordinary partial differential equation, if such thing exists. Ordinary partial differential equation. And with a random driving, but of process, but of bounded variation, and then approximate this approximation with using this general scheme. But in this scheme, the operator and everything driving is independent of time. And in approximating stochastic partial differential equation, you will have not only omega. Omega is okay, you fix omega and so, but you will also have time.
Yes, that's
So
true.
what do we do?
Yes, we we have an extension to time-dependent case as well. So we have done that, but I was afraid of formulating the more general scheme. I thought it was abstract enough to heal many people. So, but we have that, so that is not an obstacle.
No, I'm not saying that.
So are there more questions? Comments? Yeah, there's Salah, please.
Do you expect to have any quicker convergence if you are looking at weak methods?
Yes, good question. Maybe, or no. Don't know. And in fact, I should have mentioned that concerning weak convergence for SDEs, there are classical very nice results, which I should have referred. That is the results by Tubarro and Talai and also Klöden, Pladen, Hoffman, and also Maria Van, Thalmeier together. But that is concerning weak approximations, and I suppose one can do similar or maybe better results here as well. These are strong approximations, but I haven't tried. I had one experience with weak approximations, and that was quite difficult subject for me, so I haven't tried that yet.
One more.
So in your examples, I just maybe got a little confused at one point. You had this polygonal approximations, right? Polygonal approximations. Now, is that wasn't a restriction though? You didn't need to have that, or did you?
What is the question? Whether that
was? I mean, your examples were all polygonal, but the abstract structure went by too quickly for me to make sure. Was that necessary to have it, the polygonal approximations?
No.
No, it's not.
So in the first step, one can have
good one,
any approximations which satisfy those conditions I, 2i, 3i. So those conditions, that means that approximating the driving noise, second approximating the area processes, and third the kind of boundedness assumptions. And these assumptions are satisfied for the polygonal approximations, for smoothing, and for many approximations. In fact, it is difficult to construct an approximation which does not satisfy, though there are examples. So McShane constructed an example that is not satisfied.
Are there more questions? If no, thank the speaker again.